Okay, we'll give everybody a chance to get back in. Hopefully this will be a little bit better, I hope. Either that or we just are in a good prime time for everybody to be on. So hopefully this will kind of fix it. I hope so, yeah. All right. Again, we'll just give everybody a couple of minutes here to come back on before we pick back up. All right, so hopefully, again, you could hear me a little bit better, I hope, at this point. And again, we'll give everybody a minute or two to come back in. That's technology. Hear me now, cut me out later. You know, that'd be good. So somebody had a question earlier about looking at the last page. So I'll just go back on that while we're waiting for another minute or so for people to come, hopefully. All right, so why don't we kind of pick up and hopefully everybody will come back in. Okay, so we were talking again about this titration curve here. We're talking about everywhere. Once we start adding sodium hydroxide in this particular case, are really just a strong base to before the equivalence point. Again, when you go through the ice table, it will look like the one we were working through there. And because you're doing basically a weak acid and its strong base, again, you will generate basically its conjugate partner on the other side. And the ice table will always basically end up in the same sort of effect. You will always end up with a buffer at this point in the titration. So you've actually made a buffer here. So this is also one way which we were talking about when we were talking about a buffer, that you could potentially make a buffer from the combination of a weak acid and strong base, like what we got here in this problem. And the buffer, though, itself is not made up of the sodium hydroxide, but it's made up of what's left over after the reaction is done, which is what we have boxed up here, the acetic acid and the sodium acetate. So part 3 of sort of the buffer experiment that we're going to be starting is almost like this reaction right here, where we react a weak acid with a strong base. And again, the strong base is not part of the buffer, but it's able to generate a buffer as a result of that reaction. So getting back to sort of titration and pH, what you would want to do at this point is to use either the Henderson-Hasselbalch equation. Again, it's good practice to convert everybody back to molarity at the end of that first ice table, and then go into the Henderson-Hasselbalch equation. Or secondly, like I were talking about before we sort of got cut off there, if you chose to do an ice table instead of the Henderson-Hasselbalch, then the important part is, like we were talking about with buffers, you want to make sure that you got an actual number right here for the starting amount of the second guy. So usually people will leave that as 0. And again, at that point, you're not doing a buffer problem. You would be doing just a weak acid problem. So when you start this type of titration to the equivalence point, it requires at least one ice table. So anywhere in this green sort of circle to the equivalence point, it's going to require you to do at least one ice table. Again, the purpose of that ice table is really to find the concentrations of your buffer, because you will be left with a buffer at this point, no matter what combination you put together of a weak acid and strong base. And then again, you have an option. You can go right into the Henderson-Hasselbalch equation at that point, or you can do a second ice table without the Henderson-Hasselbalch and get the pH. So it really is your call at that point. whichever way you want to do it. So again, you can start to see that this type of titration is very different in terms of the calculations than the first one we talked about. So then let's talk about what happens when we do get to the equivalence point here. So when we do get to this equivalence point here, what's going to happen? So let's go back to our table there and sort of see what happens. So when we do get to the equivalence point, so at the equivalence point, we are going to have our same reaction occurring. Our acetic acid plus our sodium hydroxide. Going to give you some sodium acetate plus our water. So again, I'm just going to make up some numbers here. So we're going to start with our 4 moles of our acetic acid to begin with. We're going to know that we're at the equivalence point. So again, the definition means that we're just going to ignore the water here because it's not going to play a part in anything. So because we're at the equivalence point, what that means is the change here, you can't really mess up. It is going to be 4 moles. Going to be 4 moles here. And we're going to have plus 4 moles here. So just like what we would expect here, because we're at that equivalence point, the moles of the acid will equal the moles of the base, which means when we do get to our equilibrium, we're going to have 0 of that guy, 0 of that guy, and 4 moles of that guy right there. At this point, we can then convert it back into molarity using our total volume for the titration, which is, again, how much acetic acid in this example divided by the volume of sodium hydroxide that we also added with it to get us to molarity. Again, at this point, if you're not sure what is going on, you could use your ice table. And our ice table shows us that the only thing that we have left at this point is a salt. And we have that salt, which is sodium acetate. And again, when we think about that salt, we should know that that salt came from obviously a weak acid and a conjugate base. I'm sorry, it came from a weak acid and a strong base. And when it breaks apart, it is going to break apart into Na plus and acetate. So we do know that the sodium, which is group 1, will not go through any hydrolysis, but we do have this part of the salt that came from a weak acid, which means it's going to be relatively strong. So at this point in the titration, you actually then has to do a second ice table with the reaction of the salt, which is the acetate in this case. It is going to go through hydrolysis and react with water. Since the acetate came to we tell us 2 things. Just solution should be basic because we are producing hydroxide. We also know that when we do this, because it's basic as well. So this does need to be done in mole x plus x kb, which will give you x squared concentration at this point. It is the we're just going to have to kind of do our best with it. It is cutting in and out a lot, unfortunately. I think it's more on their side. So we're going to have to do our best to hopefully hear and do your best to kind of follow. Unfortunately, hopefully it'll come back and kind of stay instead of kind of cutting in and out like it's been doing. So at this point in the titration, I think the good news is when on the recording, it won't be choppy. So you could always come back and listen to it on the recording. I think the audio will be okay on that in that sense. So in this case, we will have the pH of our solution at this point. So at the equivalence point, it is definitely going to be a lot more calculations than the first one. it is going to definitely require 2 ice tables. The first ice table, the purpose of it is to basically figure out the concentration of our salt. The second ice table is basically a hydrolysis equation. So it is going to require 2 ice tables at the equivalence point. And it should always end up basic in this case when you're doing this type of titration. So when you do this type of titration, when you take a weak acid and a strong base, it should always end up being basic at this point, because at the equivalence point, you will always generate a salt that is really a basic salt that will generate hydroxide. So looking back at our table here, our titration curve, at the equivalence point, always going to be basic, like we kind of see in this example. Theirs was 8.72. And that again is going to require at the equivalence point 2 ice tables. First one to get the concentration of the salt, and that salt will then go through hydrolysis, which will be your second ice table that you have to do. So much, much different than the strong acid and strong base, where you just write that pH of, you write a pH of 7 and you're done. Now let's see what happens once we go past the equivalence point and we continue to sort of go past it. Let's see what happens in terms of our calculation. So when we go past the equivalence point, we will still have our equation. And again, we'll still make our sodium acetate here. And our water. And if we're past the equivalence point, just like in the other titration, the same situation is going to occur. We're going to have a switch in terms of what's the limiting and what's the excess. And in terms of the excess reagent is going to be our sodium hydroxide. Again, you're just adding the sodium hydroxide, adding the sodium hydroxide, just past that equivalence point. So if we were to kind of make up our numbers again, starting with our 4 moles of acetic acid, at this point we should have more moles of our sodium hydroxide. And that switch occurs, which means the acetic acid here will become the limiting reagent. And that means that we will end up with 0 of the acetic acid. We'll end up with 2 moles of our sodium hydroxide, 4 moles of our acetate. We have some sodium. And when you look at those two things, you can see that this is not a buffer. So very, very common at this point in the titration. People go, cool, I got like 2 numbers. I'm going to go into my Henderson-Hasselbalch equation and I'll be good. Although one's sodium hydroxide, one is sodium acetate, they are not related to each other. They are not a buffer. Again, you cannot have a buffer with a strong base. So you should not use the Henderson-Hasselbalch equation at this point in the titration. Even though you have that urge to do so because you have 2 numbers, you should not do it. So what that means when we look at what we got going on is we have our, again, I'm just making up these values. So just making up these values like I did previously, just kind of simple numbers, just so you can kind of see what's happening. So we have this salt that, as we saw in the previous step, will go through hydrolysis and will generate hydroxide. So it will be able to act as a base. But we also have this other guy over here, which is obviously sodium hydroxide, which is a strong base. And between the two, Obviously, sodium hydroxide is a much stronger base than the sodium acetate. So when sodium hydroxide goes into the solution, as we've talked about, it essentially just needs to go for a swim. It will break apart. It will generate some hydroxide really quickly, as opposed to acetate, like we saw in the previous step. It's got to go find some water. It's got to do a little bit of a reaction with water, and it needs to generate the hydroxide. So typically speaking, in this type of titration, once we reach this point, past the equivalence point, we essentially will ignore the contribution of the salt. Let's look at the contribution of our strong base in this case, as it's going to be pretty much the major contributor of hydroxide in this particular reaction at this point. And that's good, because what that means is at this point, since that is our strong base, that essentially will give us our hydroxide concentration, which will allow you to get to the POH first, subtract 14, and you could get to the pH via that route. So when we go past the equivalence point in this type of titration, again, very different than the first type of titration. It requires one ice table to be done in moles. The purpose of that ice table is to figure out the concentration of your strong base you have left over. And once you have your strong base left over, that'll allow you to get to your pH. I'm not sure I understand your question. So if you're asking why does some of the ice tables have sodium hydroxide left over, is that what you're sort of asking? And some don't. So if that's what you're asking is why when we get to a certain point on some of these parts, we do have sodium hydroxide left over and sometimes we don't. It does depend on exactly sort of where you are in the titration. So that's why it's important. So let's just go back and take a look at that curve real quick. So for example, when we look at this curve here, right, we're adding sodium hydroxide. At the very beginning, we haven't added any sodium hydroxide. So that's why in that original ice table that we did, there was no sodium hydroxide in it, because we had not started adding any sodium hydroxide at that point. Once we started adding sodium hydroxide all the way up to before the equivalence point, we will have sodium hydroxide in the ice table. So that would be like our second ice table up here on top. The difference here is we don't end with it, because at this point in the titration, the sodium hydroxide is like the limiting reagent. So it gets completely used up. So that's why we do start with it, but it does get used up by the time we're done, because we're before the equivalence point. Now, when we get to the equivalence point, which is this guy right here, it also gets used up. So we do start with sodium hydroxide, but it gets used up completely at that point as well. So that means that we don't have any sodium hydroxide left over at equilibrium at that point in titration either. So really, as you go from really the start of the titration to the equivalence point, the sodium hydroxide, or the strong base, it doesn't necessarily have to be sodium hydroxide, but the strong base in that case is sort of like the limiting reagent. It really gets completely used up all the way through that process, no matter where you stop along that curve before the equivalence point. It's not until you get past the equivalence point that there's a switch that occurs. And basically the strong acid, once you go past the equivalence point, becomes the limiting reagent, and the sodium hydroxide becomes the excess reagent, right? And that's what happened in our last table here. That is why we actually did end up with some sodium hydroxide left over, is because we're past the equivalence point, and past the equivalence point, you essentially have excess sodium hydroxide that's there. So when we're here at the equivalence point or past the equivalence point, at this point in the titration, the question was, why did we cross off the salt? You are going to be left with, from your ice table, basically two things. You'll be left with the sodium hydroxide, which is a strong base, and you'll also be left with the sodium acetate, which is a salt that will go through hydrolysis, or a basic salt. But when you're comparing those two, the sodium hydroxide is a much stronger base than the acetate would be. So the contribution from the acetate is going to be extremely small compared to the contribution of the sodium hydroxide in terms of the hydroxide that it's going to supply. Again, because sodium hydroxide is a strong base, essentially just needs to be added to that solution. So when you open up the burette and you drop the sodium hydroxide in, as soon as you do that, it's going to 100% break apart into hydroxide ions. And that's going to be a major contributor to hydroxide in that solution at this point. The acetate will produce hydroxide, but it's got to go find some water. It's got to do a little hydrolysis reaction. It's not going to be as efficient, if you want to think about it that way, in producing hydroxide. So its contribution is going to be negligible at this point in the titration, and that's why we crossed it off. It is definitely not negligible in the previous step, and that is because in the previous step, at the equivalence point, it is the only thing that's left there. So it's the only thing that's left. You have no strong base. So it is at the equivalence point the major contributor to hydroxide. But once we go past the equivalence point, the major contributor is just going to be, if you just visualize, if you've done the titration before, which I think most of you have, if you just open up that burette and just let the hydroxide flow in freely, you're adding tons and tons of free hydroxide, and that sodium hydroxide is going to be that major contributor. Any other questions? Now, while we were looking at this up here on the board, at the equivalence point, I mentioned that you do want to use the KB value, obviously, for down here. Just like in a kind of traditional hydrolysis problems, you most likely will be given the Ka value in this titration. So again, you will have to use that Kw, right? That relationship that the Kw equals the Ka times the Kb, usually to convert it. No, so remember that when we're talking about salts, basically ions in group 1 or 2, so sodium, potassium, those guys, they're neutral salts. They really won't go through hydrolysis. And the reality of reason why is, if you look at it, for example, in this titration, the sodium pretty much came from sodium hydroxide. And sodium hydroxide is a strong base, which means technically the sodium is conjugate acid, and it would be technically a weak salt that will not go through hydrolysis. So pretty much anybody from group 1 and 2 will not go through hydrolysis. There's a couple of exceptions, but a majority of ones from group 1 and 2 on the periodic table are considered neutral salts, because they essentially are derived from strong bases, is really why that is. Other questions on that? So clearly this type of titration, a little bit more complicated in terms of the calculations. The good sort of news on it is it really is all of the calculations that we have done up until this point. The thing that gives people the hardest time is applying sort of the right calculation in the right area of a titration. And that's why it's important to understand where you are in the titration, so that you can do the correct sort of calculation and understand the correct calculation as to what you should be doing. Because sometimes it's much easier to know I should be doing this type of calculation, rather than what most people do is try to figure it out sort of in the moment as they're doing the calculation. And they often will do sort of the wrong calculation a lot of times. So it's good to know, oh, I'm at this point in the titration, I should end up with a buffer, which means I need an ice table, Henderson-Hasselbalch, or I'm at the equivalence point, I should do an ice table and then a hydrolysis problem. So it's good to have those things in your head to begin with before you start the calculation, because that oftentimes will keep you from getting lost and going down the wrong end. So again, just to reiterate here, before we start the titration, all we got is a weak acid, so it's going to require a Ka problem at the very beginning here before we add. Once we start adding to the equivalence point, you will need to do at least one ice table. The purpose of that ice table will be to get the concentration of your buffer, because you will end up with the buffer, and then you can do the Henderson-Hasselbalch, or alternatively, you could do 2 ice tables in this region. I'll get your question in just 1 second. And at the equivalence point, there, it is going to require 2 ice tables at the equivalence point. First ice table will give you the concentration of your salt, and you will always generate a basic salt at this point. Second ice table is the hydrolysis ice table, where the salt will produce hydroxide. You will need to change the K value probably to a Kb value, and you could solve for hydroxide and get the POH and then get the pH. Once you go past the equivalence point, here, not all the way to the end, but anywhere here, it is going to require at least 1 ice table. Purpose of that ice table is to figure out how much excess strong base you have left over. That will get you to the OH minus concentration and then the POH. So to sort of answer your question, usually the problem will be you'll just be given the information. You need to kind of know what these charts look like. I think this titration curves look like. It will be helpful for you when you're trying to solve the problems. You do need to be able to sort of figure out, where you are in the problem. That also will be very helpful for you as well. So the problem that you probably will be given won't be like, here's a titration curve calculated at this point, this point, this point. It'll be more like the example we'll have coming up here in just a second, where you just like, hey, you added 20 milliliters of this to 30 milliliters of that. What's the pH at that point? Other questions on this type of titration? Okay. So let's take a look then at, actually, why don't you try one real quick here? Let's see what you come up with. Let's do, all right, so why don't you do the same titration. Let's say you added 21 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar acetic acid. What is the pH? So same reaction, Ka value for acetic acid, 1.8 times 10 to the. So why don't you take a minute or two and calculate that and see what you come up with, and then we'll go over it just to make sure. Okay, so let's see how we're doing here. So again, it is a titration, so we're going to need our equation here. So we're going to take our acetic acid plus our sodium hydroxide, going to get us our sodium acetate plus our water. So again, obviously, we've added 21 milliliters of our sodium hydroxide to 25 milliliters of our acetic acid. Again, the sodium hydroxide in the burette, the acetic acid in the beaker, the flask, whatever you like. We do need to do this in moles. So for our acetic acid, we're going to take 0.025, which is 25 milliliters converted into liters, times it by our 0.1 gives us 0.0025 as our starting amount here. I can get this thing to stabilize enough to write it. We're also going to do the same thing for our sodium hydroxide, 0.021, which is 21 milliliters converted to liters, times it by 0.1 gives us 0.0021 here. This would be 0. Any questions on that so far? If you're not sure where you are in the titration curve, again, you could use the ice table here to help you figure it out. Remember that if you're at the equivalence point, the moles of the acid should equal the moles of the base, which in this particular case, we're starting with this guy and we're adding our sodium hydroxide. So what we see is they are obviously not equal to each other. And what we are adding is less than what we started with. So that tells us that we are definitely before the equivalence point. So again, the ice table does have a lot of information in it. It can allow you to figure out where you are in the titration. Because you are before the equivalence point, that should also point you in the right direction in terms of the change here should be the moles of the sodium hydroxide, as it is the limiting reagent at this point in the titration. That means when we do reach equilibrium for our acetic acid, it doesn't flip pages, there you go. Our acetic acid would be 0.0021, 0.0004. And we would have none of our sodium hydroxide and 0.0021 moles of our acetate at that point. Any questions on that ice table so far? Again, it's very good practice at this point after you do the initial ice table to convert these guys back from moles into molarity. Our total volume at this point, we started with 25, we added 21, that is 46 milliliters. That means we're going to divide each of these guys by 0.046 liters. That shows up, hopefully. Divide this guy by 0.046 liters. There's like a 20-second delay in this that I write something. 0.0004 divided by 0.046. That gets us 0.0087 for this guy over here. Where we got? 0, we'll call it 87 molar. That will also give us 0.0457 on this side. And again, if you're not sure what you got going on at this point, you can use your table here. We have acetic acid. We also have a little bit of sodium acetate. Oh, big circle there, huh? And again, both of these things, if you know is a buffer. Yeah. And again, you would know that from where you are in the titration curve, because we know before the equivalence point in this type of titration, it is going to be a buffer. So again, you could do an ice table if you want, or the easier move probably is your Henderson-Hasselbalch at this point. So we're going to take our pH is equal to the pKa plus the log of the base over the acid. That means the pH equals 4.74, which is the pKa value when you take minus the log of the Ka. And that is going to be plus the log of our base, which is our sodium acetate, our 0.0457, divided by our acid, 0.00870. And if we do all that, good stuff maybe. We end up with a pH of 5.46. And it is still acidic, which also makes sense because it is before the equivalence point. And before the equivalence point, which is turns basic at the equivalence point, or it's basic in the equivalence point area. And if we look back at our chart real quick here, let's see how we did, hopefully. Didn't screw up anything. We had 5.46, which was right in this area. And that is at least between these two numbers. So that's not bad. I guess we did it all right in that case. So any questions on any part of that calculation? So I can't stress enough that how important it is to sort of visualize where you are in that titration curve, because if you know exactly where you are before you start the calculation, you should know what type of calculation you should be doing. Any questions on this type of titration curve, which is obviously very different than the strong acid, strong base titration curve? Okay, then let's talk about the last type of titration that we're going to talk about, which is this type of titration. We're going to be doing a titration of a strong acid with a weak base. Now, the setup here for this one is different. Up in the burette, actually, in this case, is your strong acid. So like your HCl in this example. And down in the beaker is your weak base. Like your ammonia in this case. Are you asking, instead of using the Henderson-Hasselbalch equation in the last example, using an ice table? I'm not sure I understand from the graph. You mean from this graph? The only place you would use it for the third ice table before the equivalence point. Yeah, so that'd be just like this one in the example we just did. You would do the ice table like normal with the sodium hydroxide. You'd be left with a buffer before the equivalence point, which you then could have two options, which I think is what your question is. You could go into the Henderson-Hasselbalch equation directly, or you could do an ice table. And if you did the ice table, it would look like over here, basically just the acetic acid breaking apart into acetate plus H plus. The important part is these initial guys would be your equilibrium values. And you would need a number here. And what most people mess up on is here, they'd put 0. But they would also need that molarity from above, and this would be 0. And then it's like a normal table with x's, plus x, and then you could solve for x. And what you would get at that point would be the concentration of H plus, which then you could go into the pH equation. So you don't have to do the ice table, the second ice table. You could do that in place of the Henderson-Hasselbalch equation, or you could do the Henderson-Hasselbalch equation and not do the ice table on that second one. So, okay, no problem. All right, so let's take a look at this one. So again, a little bit different here. We are adding our acid actually to our base. So when we start this titration, actually before we start the titration, the only thing that we have in the beaker is a weak base. So it is just a KB problem at that point before you begin. And you would do an ice table to begin with the molarity, because you haven't added any HCl in this case. These would be your minus X's, your plus X's, your plus X, your molarity minus X, your X, and your X. Because this is a weak base, obviously you would go into the KB value at that point. So much like the previous titration, it's very similar, except that in this case, we're not starting with a weak acid. We're starting with a weak base, which will require you to do a KB problem. That is also why if you look at this titration curve, it is basically flipped on its head from the last one. And that is because we are starting with a weak base, which means our pH is actually starting higher in this case. And then we're actually adding acid, so the pH will start to drop. So we're actually going downwards. It's basically the same curve, but we're starting high pH, ending low pH in this titration, as opposed to the opposite where we're starting low pH and ending high pH. But kind of the same curve going on. Now, as we start this titration, so anywhere from when we start the titration to before the equivalence point, again, just to take a look at that and see what's happening, we would have a reaction that takes place. So that's going to be our NH3 plus our HCl. That's going to get us some NH4 plus and some Cl minus. So this would be before the equivalence point. Again, just making up these numbers. So we're going to start with 4 moles of our weak acid. We're going to add our HCl to it. So again, because we are adding and we're before the equivalence point, the moles of HCl should be less. So we'll go with 2. Again, just made up. That means at this point, our HCl is the limiting reagent, gets used up. Again, the smaller number, so you don't get a, again, draw a big line I didn't draw. All right, so not so great the connection today. There we go, let's try that again. So we'll try that very shorter line maybe this time. We're going to divide each of these by the liters to get to the molarity. And you may be wondering why I did not do anything over here with the chloride. What we should know about the chloride is it is a neutral salt, right? So again, it's not going to participate really in anything. It's not going to affect the pH. And as I mentioned before, sometimes it's best not to put values in where you might want to use them. But if you do look at what's left over at this point, we have some ammonia and we have some ammonium. And hopefully you could recognize that these two guys are related to each other. That is a weak base and its conjugate acid. That again is a buffer. So much like the last one, before the equivalence point, you are going to be left with a buffer. The main difference is this buffer is actually a basic buffer, but it really doesn't matter. You would still probably want to use your Henderson-Hasselbalch equation, or again here you could do an ice table, much like what we talked about previously. But probably the easier move would be to use the Henderson-Hasselbalch equation to get to the pH at this point. So this one, very similar to what we were just talking about in the previous titration. The only difference is really you're going to end up with a basic buffer at this point. And we can see that from the actual curve because we're still basic at this point. So you'll end up with that sort of basic buffer through here. So just like the last one, anywhere where you start the titration before the equivalence point, going to require one ice table minimum. The purpose of that ice table is to figure out the components of your buffer. And once you do, you can go into the Henderson-Hasselbalch equation. Again, you could also do an ice table. That is absolutely right. The Henderson-Hasselbalch equation is really only for a buffer, which is that common ion situation, which means you technically should have a combination of either a weak acid and its conjugate base or a weak base and its conjugate acid. So as we talked about before, you should not use the Henderson-Hasselbalch equation everywhere. It is only specifically in that buffer sort of situation, which is really a common ion situation. The alternative to that is you don't have to ever use the Henderson-Hasselbalch equation. If you like ice tables better, you can do an ice table instead of using the Henderson-Hasselbalch equation, even with buffers. Other questions on that? So that brings us to what happens here in our equivalence point region. And in our equivalence point region, let's see what happens here. Again, we're just going to make up some numbers at the equivalence point. We're going to again have our reaction, same reaction taking place. We got that. Again, making up the number, starting with 4 moles of our NH3 in the beaker. Because we were at the equivalence point, that means we should also have 4 moles of our HCl there. We will have 0. Change is going to be, can't pick the wrong number since there's only one number. It's going to be -4, -4, and +4 in this example. And again, that is because we're at the equivalence point. As we see here, which means because it came from a weak base, we should know that it will go through hydrolysis. So much like the other sort of one that we were looking at, when you reach the equivalence point, it's not going to require one ice table, but it will require 2. And that second ice table is going to be the NH4 plus reacting with water. And when it does, it is going to act as an acid, which means it's going to donate the H plus over. When it does, it will make NH3. Plus some H3O plus. And again, without doing any calculations, we should know this is going to be acidic dissolution. Also should tell us a Ka we should be using as well in this titrate from the first table. This is which would get us our X, means you then could go directly into the P. So it's very similar to the previous titration at the equivalence point. You will need 2 ice tables. The first one will be for the purpose of getting the concentration of the salt. You will always generate an acidic salt at this point, which will go through hydrolysis like in the second table, which you also has to do. And you do want to do it in molarity, that second table. And you will generate basically H3O plus, which means it's going to be acidic. You're going to have to use Kw to get to the Ka value. Once you solve for the H plus concentration, that is going to be what X would equal, and then you could go into your pH. Any questions at that point in the titration? So just to sort of finish up talking about this type of titration, let's look at the last part of it, which is also very similar. So at the last part, after the equivalence point and on, to take a look at what's happening there again. We are going to have our reaction. So initially, if we had our 4 moles of this, which is what we're starting with, and this is what we're adding. Again, if we're past the equivalence point, we have that switch that occurs, and our NH3 in this case would become the excess reagent, which also means that our strong acid becomes the limiting. I think I did that backwards. Huh? I got that backwards in my head. Sorry about that. Hang on. I wrote it backwards, this equation here. So that's not right either. We're actually starting with the NH3. All right, take 2 today. We're starting with the NH3. And we are adding our HCl. There we go. All right, so we would start with 4 moles of our NH3. We would have 6 moles of our HCl, which is more. Again, the NH3 would become the limiting reagent, so it would be -4, -4, and +4 moles. And at equilibrium, we would end up with 2 moles of this guy, 0 of the NH3, and 4 moles, which, like normal, we would want to convert back to molarity using our total volume. And again, when we look at what's left over at this point, we have NH4 plus. People screw up because they go, I got 2 numbers. I'm going to use my Henderson-Hasselbalch equation. You don't want to do that. These 2 things are not related to each other. They're not a buffer at this point. We do have a similar situation as before. We have our salt over here that will go through hydrolysis and act as sort of an acid. But we also have, which is a strong acid. And much like in the last titration, in comparison, we will ignore the contribution of the salt in this case, because much like the strong base, the HCl just needs to go for a swim and it will make H+. So it's a much stronger acid. And that means that at this point, because this is a strong acid, that will give us our H+ concentration. And we could get directly from it our pH at that point. So this titration curve, although it is kind of backwards of the previous one we talked about, it's pretty much the same types of calculations that you have to do along the way. And just to review this one here, the only difference is we're starting at a high pH because we're starting with a base and ending at a low pH. But before you begin, like the last one, which was a Ka problem, this will be a Kb problem because, again, we're starting with a base. Anywhere from starting the titration to before the equivalence point requires at least 1 ice table done in moles. The purpose of that ice table will give you the concentrations of your buffer components. That buffer will be a basic buffer. And again, probably the easiest way would be to do a Henderson-Hasselbalch equation at that point. When you reach the equivalence point, requires 2 ice tables. First ice table done in moles. Purpose of the first ice table is to figure out the concentration of the salt that will be left over. That salt will always be an acidic salt, which then will go through a hydrolysis reaction, which is your second ice table. That should be done in molarity with X's. When you solve for X using the Ka value, you will get the H+ concentration that then can go into your pH equation. And lastly, after the equivalence point, you're essentially just opening the burette and adding a bunch of strong acid. And that means that you need 1 ice table. Purpose of the ice table is to figure out the concentration of the strong acid that's left over. And once you do that, you could go into your pH formula. Any questions on this type of titration? Okay. Okay. All right, so let's just talk about the rest of the day here. So we went a little bit over with some technical difficulties here today. Um, so we're going to officially kind of stop lecture right now for the moment. And the next thing that you should have, and I'll put it back to this page in just a second here, is this example here that will walk you through basically the different parts of a titration problem, similar to sort of problems like you would have obviously on the exam and quizzes and all that good stuff. So what I think we're going to do is we're going to take maybe like an hour and 10-minute break. You should work on that example. So instead of starting lab at 11:30 like we normally would, we'll start it at 12:30. That way I'm not just sitting with you while you're working on it, I suppose. So you could work on it in the next hour and 10 minutes, an hour and 15 minutes. I will start the lab section at about 12:30-ish. We will go through that example just to make sure everybody is on the same page on how to do these titration problems. We will also, after we go through this example, be pretty much done with this chapter. We will then talk about the buffer experiment that will be up online very shortly as well, and sort of what you need to do on that one as well. So we'll talk about that experiment. We will also assign sort of buffer values that you need to do for that as well. So since we're kind of at an example and sort of a long sort of example, there's 4 parts to this example here, 4 different points in the titration. Why don't you take the next hour and 10 minutes or so and work through it. Take a little break if you like before then, and then obviously work through it. And then again, I'll start the lab about 12:30, 12:35, and we'll go through this example. Once we're done with this example, like I said, that's pretty much most of this chapter. And then we'll get into the buffer experiment. Any questions on any of that? Okay. Do you have a question on the pH and hydrolysis? Yeah, you're gonna have to look up K values. Normally when we do the experiment, you have to look them up as well, like in your book or something like that, or some type of resource. You know, in the real class, we have the lab. We have the bookcase. It has all the like chemistry books in there and stuff like that. So you may have to look up the Ka or Kb values in the book. Yeah, in a book or some type of resource that you have and stuff like that for sure. Okay, any other questions on that? And a reminder, that is due, I think, towards the end of the week, right? Is that pH and hydrolysis one? So make sure you're working on that as well. But I think we'll take this break, work on this example. We'll come back in about an hour or so with the lab lecture. So come in through the lab one, and we'll go through this one just to make sure everybody's on the same page for titrations. And that will set us up for next week when we're talking about titrations and stuff like that, are doing the experiment for titrations. And then we'll talk about the next lab, which is the buffer lab. So we'll reconvene about 12, I'll call it 12:40 at this point. About 12:40, we'll reconvene in the lab and we'll go through all this type of stuff. Any questions on any of that stuff? Okay, I'll see you in about an hour and 20 minutes in the lab lecture.